Hello everyone, thank you for watching this video. I'm Chong Shangguan. I will talk about the combinatorial list decoding problem of Ritz-Solomon codes. This is based on a joint work with Zaki Tamo. Both of us are from Tel Aviv University. For simplicity, I will restrict our attention to linear codes. So a code is a vector subspace of FQ to N with dimension k. Here FQ is the finite field of Q elements and N is the code length. And I will call a vector in C a code word. The rate of a code is defined by R equals K over N. For two vectors x and y, the Hamming distance dxy is the number of distinct coordinates between x and y. Here xi is the ith coordinate of x. The minimum distance d of the code is the minimum of dxy among all parts of non-equal code words x and y. The minimum distance of a code is related to its unique decoding property. To state it, we will need the notion of a Hamming ball. For an integer r and a vector x, the Hamming ball of radius r and the center x is the set of vectors that have Hamming distance at most r from x, and we denote this set by brx. It is clear that the Hamming distance satisfies the triangle inequality. Using inequality, one can easily show that for any vector x, the Hamming ball of radius d-1 over 2 and the center x has at most one intersection with the code C. Here d is the minimum distance of the code. Given this formula, one can define the following unique decoding algorithm. Given received vector x, we seek for the code word that is closest to x in the Hamming distance. If the channel introduces at most d-1 over 2 errors, then the decoder would output the unique code word in this intersection. If the channel introduces more than d-1 over 2 errors, then the decoder may output failure. The unique decoding property clearly characterizes the error correctability of a given code. However, instead of outputting failure, we still want to say something meaningful where the number of errors is more than d-1 over 2. For this purpose, Ayers and Wozencraft independently introduced the notion of list decoding. To be precise, for a real number rho belongs to 0 and 1 and an integer L, a code is called rho, L list decodable if for any vector x, the Hamming ball of radius rho n and the center x has at most L intersections with the code C. Put it differently, if the channel introduces at most rho n errors, then the decoder would output a list of at most L code words, which include the correct one. We further call rho the decoding radius and L the list size. It is clear that list decoding is a generalization of the unique decoding. There are basically two types of questions in list decoding. The first is the combinatorial question, which asks for which parts of rho and L a code is rho, L list decodable. The second is the algorithmic question, whose goal is to design an algorithm that efficiently output the list of code words in this intersection. Therefore, L should not be too large, and it is required that L must be bounded from above by a polynomial function in the code length n. In this talk, we will focus on the combinatorial question and study the list decodability of Ritz-Solomon codes. Next, we will give the definition of a Ritz-Solomon code. Let alpha be a vector whose n coordinates alpha1 to alpha n are all distinct. A code word of an NK-RS code is given by the length n vector f alpha1 to f alpha n. Here f is a polynomial with coefficients in fq and a degree less than k. Because there are in total q2k such polynomials, so an NK-RS code has q2k code words, and therefore has r equals k over n. Moreover, by the fundamental theorem of algebra, one can show that the minimum distance of an NK-RS code is d equals n minus k plus 1. We further call alpha the evaluation vector of the code, and we say that the code is defined by the vector alpha. RS codes are important in both practice and theory. On one hand, it has many applications in data transmission, broadcast system, and modern storage system. On the other hand, it is an important research object in both coding theory and theoretical computer science. Later, we will introduce the fundamental limits to list decoding RS codes. When speaking about list decoding RS codes, we must mention the celebrated work of Goswami and Sudam, who showed that one can efficiently list decode RS codes up to radius 1 minus square root of r. This radius is the commonly termed Johnson radius. Since then, it has been a long-standing open problem in the field to determine whether RS codes can be list decoded, either combinatorially or efficiently beyond this radius. However, after 10 years of the work of Goswami and Sudam, there are two results which indicated that RS codes may not be list decoded beyond this radius. The first result is due to Chen and Wang, who showed that one can reduce the problem of list decoding RS codes to the list log problem, which is a hard problem in cryptography. And then they show that if one can efficiently list decode the Solomon code to some radius, then one can also solve the discrete log problem efficiently. The second result is due to Bensassin, Kompany, and Red-Kirshner. Loosely speaking, their results showed that there are no such codes for Q equals n. An RS code with Q equals to n is two sets have 4 lengths. And the result showed that to beat the Johnson bound, we need to have at least Q larger than n. On the other hand, a recent breakthrough of Roger and Wouters in 2014 showed that there in fact exist some RS codes that can be list decoded beyond the Johnson radius. This is a very surprising result and applied truths from high-dimensional probability theory. However, there are 3 shortcomings of the result. First of all, the rate for which their construction can beat the Johnson radius goes to 0 as the L-fifth size Q increases. So basically, they beat the Johnson bound for a low rate. Secondly, their construction is non-explicit and is only an existence proof. Lastly, their construction is not tight in terms of the relation of the code rate, decoding radius, and the list size. Fortunately, we are able to give 2 constructions which solve all of the 3 shortcomings mentioned previously. Our first construction is the following theorem, which states that for large Q, most RS codes are 2/3 times 1 minus r, 2 list decodable. Here, large Q means that Q is an exponential function of n. And it is very surprising that the list size of our code construction is a constant too. Besides, our code has the following 3 advantages. First of all, since 2/3 times 1 minus r is larger than 1 minus square root of r, which is the Johnson radius for r larger than 1/4, then this means that our construction can beat the Johnson radius for the high rate. Second, we obtain the first explicit construction in the literature for RS codes that can be list decoded beyond the Johnson radius. Note that this theorem is an existence result and provides no explicit construction. In our paper, we show that if we allow Q to be even larger, say Q to be a double exponential function of n, we are able to give the explicit construction. Finally, our construction is tight in the sense that we obtain the exact relation between the code rate, decoding radius, and the list size. To convince you, in 2 slides, we will give a marching upper bound on the decoding radius in terms of the code rate and the list size. Our second construction shows that for large Q, most RS codes are 3/4 times 1 minus r, 3 least decodable. It is easy to show that this construction beats the Johnson radius for R larger than 1/9. And we can also obtain an explicit construction of such codes. And the bond is also tight in terms of the relation of R, rho, and L. Next, I will present the promised matching upper bound, which states that if Q is larger than L and the code is low, L least decodable, then its decoding radius cannot exceed L over L plus 1 times 1 minus R. This bound holds for linear codes, and for nonlinear codes, we can prove a slightly weaker upper bound. Setting L equals 1, we have a rho is at most 1/2 times 1 minus R, which recovers the singleton bound for unit decoding. If L equals 2, we have rho is at most 2/3 times 1 minus R, and we know that this is tied by our first conjunction. Starting L equals 3, we have rho is at most 3/4 times 1 minus R, and we know that this is also tied by our second construction. Due to the limitation of time, I will only give a proof outline of this result. Recall that an RS code is defined by its evaluation vector alpha. We say that the evaluation vector alpha is bad if the NKRS code defined by it does not have this least decodability. Therefore, to prove this theorem, it suffices to show that the number of bad evaluation vectors is at most CNK times Q2 n-1. Indeed, since the evaluation vector is a vector with n distinct coordinates, so the total number of evaluation vectors is of the order Q2n. If we manage to show that the number of bad vectors is of the order Q2 n-1, then for sufficiently large Q, most vectors are good, and therefore define RS codes with the desired property. To prove the desired upper bound on the number of bad vectors, we construct a family F of non-zero polynomials with the following 3 properties. First of all, the size F is small. Here small means the size of F is bounded from above by a function of n and k, which is independent of Q. Second, for each polynomial h in F, the degree of h is also small. Most importantly, we show that every bad vector F must satisfy this formula. It is in fact a fancy way of saying that for every bad F, there must exist a polynomial h of the family such that h alpha is 0. Using this property, it is easy to say that to find the upper bound on the number of bad evaluation vectors F, it suffices to find the upper bound on the total number of zeros of the polynomials in F. To do so, we may apply the well-known Schwarzschild lemma, which states that a bounded degree polynomial has only a limited number of zeros. Since F is only a small family of bounded degree polynomials, the total number of zeros of the polynomials in F is also small, which can be bounded from above by Cnk times Q2 n-1, and we are done. It is clear that the core of the proof is the construction of this family F. In fact, we construct such a family by proving a new type of linear dependency between code words of a code that are contained in a small hummingbird. To be more precise, if the RS code defined by F does not have this decodability, then it means that there is a vector x such that the hummingbird of radius 2/3 times n-k and the center x intersect the code in at least 3 code words, C1, C2, and C3. Then, since the 3 code words are contained in a relatively small hummingbird, they must have many equal coordinates. Our main contribution is that in our paper, we developed a technique that can convert such combinatorial intersections to certain algebraic dependencies, which states that The above evaluation vector F must zero out the determinant of some matrix. Therefore, we set the family F to be the determinant of a family of variable matrices x1 to Fn. The details of the proof can be found in our paper. In the next few minutes, I want to say something about approaching the list decoding capacity. We know that the decoding radius for unique decoding is 1/2 times 1 minus r, which can be improved to 1 minus square root of r by the Johnson bound for list decoding. And we further improve it to 2/3 and 3/4 1 minus r. But there is still a gap from the list decoding capacity 1 minus r. It is a very interesting question to ask whether our S-codes can finally achieve the list decoding capacity. More precisely, we have this conjecture which states that this bound is always achievable by our S-codes. If the conjecture holds true, then one can show that we can beat the Johnson bound for r larger than 1 over L squared. Here, L is any constant larger than 1. Moreover, setting this formula to be 1 minus r minus epsilon, and we can solve for L equals 1 minus r minus epsilon over epsilon, which means that some RS codes can achieve the least decoding capacity. We are currently working on this conjecture. To do so, we have introduced a variety of new tools which have not appeared in a study of list decoding previously. This includes the intersection matrices, which is a new notion introduced by ourselves, and the cycle space, which is a notion from graph theory. Moreover, recently, with Jerry Guo, we show that this conjecture is closely related to the Nash-Williams-Tutt theorem. This is a theorem that tells you how to obtain each disjoint spanning trees of a given graph. I will finish this talk by mentioning a list of open problems. First of all, our bounds hold only when q is an exponential function of n. Is it necessary, or our bounds holds in fact for a much smaller field size q? For example, q is only a polynomial function of n. Second, does there exist an efficient list decoding algorithm for our code conjecture? I think this is a very interesting and meaningful open problem. Last, is this bound always tight? And we only proved it for L equals 2 and 3. I think all of those are very interesting problems, and you are welcome to work on them. My talk ends here, and thanks a lot for your attention.